translating the Cantor set by random.
Is it a fried egg?
It's a scrambled egg. Yes. Yeah, so I decided instead of translating the Cantor set by random, I was going to translate the hexagram number 42 from the I Ching. I'm just kidding. So there's but it kind of looks like it, right? So this Cantor set is just a bunch of numbers in the unit interval, which only have zeros and twos in their binary expansion. So, what's that? Tertiary. I'm sorry, that's a typo, or whatever came out of my mouth is wrong. So you just you can get it by taking out all the ones, which is, in the first decimal place in the first step, and all the ones in the. You just keep taking out the middle third, and what you get in the limit is a Cantor set. So the question is, you take a Cantor set and you slide it over you add it to a Martin-Liff random real, just normal addition, and then, what do you get? What sort of points lie in there? In particular, can the points in the Cantor set cancel randomness? So that's sort of the question. And, the answer is yes. In fact, there's a lot of them that cancel this randomness. It turns out that if you look at all the sets that have a particular effective dimension in the translated Cantor set, that you get kind of a classical fractal that would be okay for normal analysts. And I guess the reason seems to involve additive number theory, so that's what I'm going to try to explain now. So I just review classical Hausdorff dimension for a moment. If you take a subset E in the real line, I let this is how you denote diameter of a set E, the maximum distance between any 2 points in the set E. And then if you take a class of reals G, you say it covers E if its union contains E. And if each of the guys in the G is a delta mesh if every member of G has a diameter at most delta, so that everybody who lives in the class G is relatively small diameter. Okay, so here's the definition of H beta measure. First I have to define this function here, which so basically you sum up over all the G's that are in your covered G and raise the diameter of the beta power. So you find the least sum that covers E, like of this form, which is a delta mesh, like I said here. Okay, so the beta dimensional Hausdorff measure of E is the limit as this function goes to 0. This is a little strange, but it seems a very standard definition. And for some reason, not too deep, but the dimension is equal to, there's actually a point where it switches from infinite to 0. So this is the place where that happens is called the Hausdorff dimension of the set E. Okay, so we can effectivize this notion by insisting that the covers are effectively open classes. So the effective Hausdorff dimension is, which I call C dim H, is the same as its classical counterpart, except the covers are effectively open classes. Okay, so you can define equivalent definition for effective Hausdorff dimension in terms of Kolmogorov complexity. So this is why I think this is even maybe an improvement over the classical notion, because there are some other forms which actually seem sensible, certainly in terms of randomness. So you can say that in fact, a single point can have a positive effective Hausdorff dimension. So the dimension, constructive Hausdorff dimension, I call it effective. The effective Hausdorff dimension of a singleton point is the lim of the Kolmogorov complexity of the first n bits of that real written in, let's say ternary base divided by n. So you look at, and then the other property is that if you take the supremum over all points of the constructive dimension of all overall points in a given set, then you get the constructive dimension of the whole set. So in particular, well, if you have a Martin-Liff random real, the Hausdorff, classical Hausdorff dimension is 0, but the constructive Hausdorff dimension is 1. This follows immediately from the definition, but the opposite is true. You can have is not true, I'm sorry. You can have a singleton which has constructive Hausdorff dimension 1, but is not a Martin-Liff random real. And so you can get things that are in between pretty easily too. So a real which is consisting of a Martin-Liff random real interleaved with a computable real has constructive dimension 1/2. So you just interleave the digits and you can dilute the dimension of a singleton point. Okay, so this is a theorem. You can actually get real classical fractals from looking at effective constructions like this. So, for example, the set of reals with constructive dimension alpha has both effective and, in fact, classical Hausdorff dimension alpha. So the first part is sort of immediate from the previous slide, but you can get a little bit more than that in the classical case as well. So I'm going to use this notation here. A plus B, if A and B are sets, this is the set of all points A plus B, where A is in A and B is in B. Okay, so the dimension of the Cantor set doesn't seem to matter too much which sort of dimension notion you use to calculate the dimension. The packing dimension, upper box counting, lower box counting, constructive Hausdorff dimension, they all give you log 2 over log 3. So that's a magic number. And in another fact about the Cantor set, which is sort of useful here, is that any real in the interval 0, 2 can be written as the sum of two members of the Cantor set. And this is slightly easier to see if you first divide the points in the Cantor set by 1/2, so that you get all the points which are either 0 or 1 in their ternary expansion. Because then you know that any point which is a ternary expansion is either 0, 1, or 2, so you either take 1, you could just do it digit-wise. You can take a 1, if you need a 0, you take both zeros. If you need a 1, you take a 1 and a 0. If you need a 2, then you take 2 1s, something like this. So I guess in particular, adding two numbers from the Cantor set suffices to completely cancel randomness, because you can get any point. So you just take a little imagination. It's actually subtraction here and not addition, but that is the principle here. Okay, so let's see. So I'm going to introduce, I think, the last bit of notation here. E equals alpha is the set of reals whose constructive dimension is alpha. Okay, and so using sort of a hybrid of the notation on the previous slide, the Cantor set plus real number r is the set of all x plus r, where x is in the Cantor set. And so we're going to be interested in looking at the intersection of these two sets, because this is translation of the Cantor set, and now we're looking at sort of the points that have various dimensions. So the main result is the following. So if you take an alpha whose classical Hausdorff dimension is between 1 minus log 2 over log 3 and 1, then for any Martin-Liff random r in 0, 1, you get the classical Hausdorff dimension of the translated Cantor set restricted to all points of constructive dimension alpha is exactly alpha minus 1 plus log 2 over log 3. Okay, so this gives an example of a set, or a class of sets, I guess, when you change with parameter alpha, where the difference between the effective and classical Hausdorff dimensions is exactly 1 minus the dimension of the Cantor set, 1 minus log 2 over log 3. Okay, so slight variation of definition. It's a little easier to look at this one first. So let E less than alpha be the set of all reals with effective Hausdorff dimension at most alpha. Okay, so let's look at this set for a second. So I look at this, do the same trick here, take a C and translate it over by X and intersect it with all of the points with constructive dimension at most alpha. Okay, so this is, I try to give some intuition why this theorem was true. That's why I'm looking at this set. But let's first, instead of trying to do the equality, do less than or equals to, because it's slightly easier. So we take a gamma being bigger than log 2 over log 3 plus alpha. It turns out that Bx is the vertical fiber of some set B, which has constructive dimension less than gamma. So then you can apply this Fubini type inequality for Hausdorff measures, which gives you that inequality. It's equal to 0. So that means for there exists, you can read from this that the Hausdorff dimension of this vertical fiber is at most gamma minus 1, which is alpha minus 1 minus dim hc for Lebesgue measure almost all x. And if you, remember from the previous slide, this is the quantity we were interested in here. So that's from an analyst point of view to why you might think this is good. But there's still a problem, even though it's true for almost Lebesgue Lebesgue measure almost all x. It doesn't tell you anything that it's true for all Martin-Liff randoms. And also you still need a lower bound in the other direction, or an upper bound, I guess I should say. Lower bound. Okay, so let's see. So here's kind of a naive idea how you can first let's try to find a point which has low constructive dimension. So I'm going to show how you can get a point within 2/3 of optimal, which is pretty simple. Okay, so first of all, you can calculate the if you just take any point in the Cantor set and a Martin-Liff random real and you add them together, the dimension has to be between 1 minus log 2 over log 3 and 1. So the question is how close to, so it's easy to get the top end. If you take your point x to be 0, then the Martin-Liff random real already gets you the right-hand side. So how close can you get to the bottom? This is the question. Okay, so take let's take R be any real with ternary expansion R1, R2. Okay, so and then you can define another set T like this. Actually, this is going to be another kind of a unfortunate page break here, so I'm going to copy this. Let's see. Okay, so basically you change all the, I think this should, so you change, this is kind of a little bit flipped around, but you take all the zeros and change them into ones and twos and leave the twos as they are. I just realized, I think the slides is...
No, we can just get rid of zeros by replacing them by twos, adding Cantor. So we can make a number which doesn't have zeros anymore.
That's not what it says in the system.
Yeah, I think... What do I want
Backwards zeros turn to ones.
to do? I want to get it, whatever it is, I want it to, it ends up like this. So you get, so you get 2/3 of the things end up being twos, and 1/3 end up being ones. You can, it's a homework problem, figure out what the other one was supposed to be, but if I had 30 seconds, I would figure it out for you right now. So the constructive dimension of, yeah. So there's a theorem due to Jack Lutz, which says that the constructive dimension of a thing which has, one, 1/3 ones and 2/3 of them are twos, is bounded above by the entropy of the string, with this property, which is entropy is given by this formula, which is 1 minus 2/3 of the constructive dimension of the dimension of the Cantor set. So this is how you can get within a point within 2/3. You just sort of this point t, which is in the Cantor set. So the t's it gives you within a factor of 2/3 of optimal cancellation. Okay, so this seems to be a bit of a bottleneck. So the question is whether you can do better. Okay, so suppose that you had a set of reals E with low effective Hausdorff dimension and the and also that when you add all the points in E with the Cantor set, you get all the numbers between 0 and 2. So for any real in 0, 2, there's an x in. Okay, so right. So for any real in 0, 2, there's an x in the Cantor set and a y in E, so that x plus y equals 2 minus r. So it's any point in 0, 2 can be written in the form x plus y. So and you have, that means x plus, you rewrite this and you get x plus r is in 2 minus e, and this means that the constructive dimension of x plus r is less than or equal to the constructive dimension of e. So the question is, how small can you make this, the constructive dimension of this set E to be? Because if you make that smaller, then you can get the constructive dimension of the sum of the points x plus r. So we're looking for a set which sort of a complementary set to the Cantor set, where you add it to the Cantor set, and then you can cover the whole interval between 0 and 2. Right? And covering the interval between 0 and 2 is the same as if you divide by 2, covering the same between 1/2. So this is kind of a useful observation. Okay, so let's look at an example here. So take C2. Let's let C2 be, this is 1/2 the Cantor set, but I've written it instead of just 0 and 1, I wrote it in pairs of pairs of digits. So it's still the same thing, but I just wrote it a little strange, I guess you can say. So now let's just consider this other set, which I've broken into blocks of 2, which I call B2, which is 0, 0, 0, 2, and 1, 1. And now we take our set E to be all the decimal expansions, which can be written as sequences built out of blocks from these 3 sets. So, you can get stuff which is 0, 0, 0, 2, 1, 1, and just concatenate them together to make it a real. Okay, so then actually we can cover the whole real number by adding points in this set E and this set I wrote 1/2 E, but I guess it should be this should be a 1/2 E up here. Okay, so I highlighted here the first place that gets interesting here, which is to say you can write, any ternary block of length 2 can be written as a sum of elements from one and the other. So in this example, you get I just copied this over. So this is an additive complement to the Cantor set. So for any beta greater than 0, you can uniformly cover E with B2 to the n intervals of size 3 times 3 to the minus 2n. And in fact, there are size B2 blocks choices for each of the first n blocks of numbers e. I'm just explaining why this is true. And the closed interval of length 3 times 3 to the minus 2n covers all possible extensions. And so then if you look at the 1/2 h to 1/2 measure of e, you get it. A calculation shows that it's less or equal to 1/3. So we got a little closer to the optimal lower point. So try to see whether you can actually get optimal blocks here. So the question is, can you decrease the effective Hausdorff dimension of E by using even larger blocks? Okay, so these are some larger blocks. In fact, they're optimal for each of these lengths. I'm very proud that we are able to compute up to B5 here. I think that finding an optimal block for B6 is probably outside the realm of feasible computation based on what computers we have available today. But it might be just that, as was the case for B4, that you take the cross product of B2 and B3, and that gives you an optimal block for length 6. So I don't know. It's so this is going to be very interesting because we'll be able to prove that you can get. I guess a challenge would be to actually explicitly construct a better complementary block to the Cantor set, which beats the best one up here, which is B3. And I'm about to show you how a theorem that lets you do better than this, but whether you could actually find such a thing in real life is an interesting question. And one of the tricks we use here, I need to look at density here for a second. So you have the density of a set A is the limit as n goes to infinity of the number of elements of A up to n divided by n. So it's the sort of the ratio of guys up to n that contain members that are members of A as you go up to infinity. Okay, so here's how you can get optimal blocks for this. So this is an old theorem from additive number theory, I guess you can call it, due to G.G. Lorentz. So there's some constant c such that for any integer k, if you have A being a set of integers, these are integers now, so you take some integers in 0 to k, and this is the size that A has to be bigger than 2. Okay, so then you can find a complementary block B living in the integers between minus k and k, such that when you add the bits of A and B together, you cover the whole interval in 0k. But the B can be kind of small, so this is what the theorem says. The B is less than c times k divided by log of, well, L is basically the size of A, log size of A over A. Okay, so Lorentz's, the proof actually solves a conjecture of Paul Erdős, which was to say that every infinite set A has a complementary set B of density 0. So that's sort of an interesting point. So here, I'm going to say the theorem is that there exists a uniform sequence. By using this lemma, we can actually approach the lower limit. We can get a point of really low constructive dimension. So there's a uniform sequence of computably closed sets. In fact, there can be computably closed, E1, E2, which is what you get by doing these interval constructions, such that 1/2 the Cantor set plus 1/2 of E sub n is the whole unit interval for all n, and you get arbitrarily close to the lower limit. And you can actually achieve closer to the lower limit. Now I want to show a little bit how Kolmogorov complexity comes into the picture here. And this is by achieving a, so you look at the lower bound for a second. So this is, you let R be any real, not necessarily a Martin-Löf random. And then this is, you can show that the Hausdorff dimension of the points with constructive dimension less than alpha in the translated Cantor set has dimension at least alpha minus 1 plus dimension of, log 2 over log 3. So so now I apply this sort of density construction to the picture here. So you take C sub A to be the set of reals which have a ternary expansion whose digits are all 0, 2, but the 2's can only occur at positions in this set. And this set turns out to have density 1 minus alpha divided by log 2 over log 3, and it has low Kolmogorov complexity. So that's sort of an important factor. So then you can actually get a complementary set which has constructive dimension alpha and also still is completely complementary to Cantor set. So what we did before the Cantor set, I'm now doing with some subset of the Cantor set. And I think since I'm getting close to the end here, I'm going to skip this proof and just look at some open problems here for a minute. So this was just a restatement of the theorem, main theorem. If you look at a translation of the Cantor set and intersect it with points of either constructive dimension alpha or less than or equal to constructive dimension alpha, they have this, the dimension is alpha minus 1 plus log 2 over log 3. So the questions: how much can the randomness of a Martin-Liff random R be reduced by adding a Cantor set point if R was not completely random to begin with? So suppose it had, instead of having constructive dimension 1, it had constructive dimension 1/2 or 1/4 or whatever. So what sort of cancellation can you do or not do in that case? And what happens if you look at other fractals besides the Cantor set? Cantor set's kind of a nice canonical example, but there's certainly other fractals you can look at. And then you can also look at other measures of dimension. So I here focused on Hausdorff dimension, but you could do packing dimension or other things like this. So there's a few sorts of questions that are maybe interesting. So, all right, thank you very much.
Questions? Sasha?
So I'm sorry, I'm still a bit confused by the main statement. So you take a random element.
Yes.
And you translate it by a Cantor set.
Yes.
And you look.
No, you take a Cantor set and translate it by. Well, I guess it's the same.
Okay.
Yeah. Okay.
Translate by a random element.
Yeah. Yes.
So you get a shifted Cantor set.
Yes.
And you look on the possible dimensions of the elements of this set. Yeah?
Right. Yes.
So what is possible and what is not? Can you repeat the answer? Just
Yeah. I had that.
Well,
This. Let me go back here. It is the rate. Well, I went too far, didn't I? This is the. This is where the range of possible.
No, but this is just for 1x. But you take the entire Cantor set.
Yes.
You translate it by random R.
Yes.
And you get a set.
Right.
Some elements will be random because
Yeah,
there
the
is
zero.
0 plus R.
Yes.
Some, as you proved, some elements will be not random.
Right.
So there is so you get some spectrum of possible dimensions of this of this shifted Cantor set.
Right.
So the simple question: does it depend on the random element or not? I still
Well, yeah.
follow.
Oh, I see what you mean. Yeah, it will depend on the.
So some random are good and some random are.
No, Tom. It works for every random, but you might need a different point in the Cantor set to do the cancellation.
We have entire Cantor set.
Right.
We shift it by some random R.
Yes.
And we look at the spectrum in terms of dimension on the spectrum of resulting set. What dimensions have their elements? So
Yeah, you get all of them for any R. You get all of them.
Any
any dimension in that range.
Yeah, you can achieve any point in that.
So for every random, the spectrum will be entire segment.
Yes, you get all of the.
No, but it's not said here.
Yeah, it's not said here.
But you get the entire segment.
It's said in the
Okay.
end.
Just
Yeah.
But those are the possible things that he's proving that.
So this actually shows that there's a lot of them. We actually construct a Hausdorff dimension of all such points. So for any, if you want to find points which have dimension, well, say alpha minus 1 plus dimension h, there's a whole lot of them because they actually have, they have.
So for Cantor set, we just have the same interval for the same dimension spectrum for every shift.
Yes.
And
that's
for
correct.
other closed set, it's also the case or not?
For every closed set?
No, other closed set, not Cantor set, but some others.
Oh gosh, I don't know. I have not looked at closed sets in general. I really.
Or just a very simple question. We take a random. Is there a closed set which applies being shifted by any random point contains only random sequences? What are the sets? Which conserve randomness. Closed set which conserve randomness. Of course, with finite set.
Yeah, finite set is a good example. You can do it. Yeah, the rationals works, but it's not closed. It's not closed.
It's a
not
very
closed.
complicated question, because, for instance, if you take two random numbers and you just add them up, the result is not necessarily random.
Of course.
You need independence. So,
No, but I want that one of the set will be closed, effectively closed.
okay.
So it cannot
Okay, yeah.
contain random. It cannot be normally.
But
surely
I don't know. I don't think you can have general results for effectively closed sets so easily. You can look at simple objects like intervals, but then of course the answer is trivial that you get every possible value. But I think what they've done is kind of they took one and it took them a while. It's not a simple proof to get the answer just for Cantor. So I don't know how much you can generalize. It's a very open question, I would say.
No, but there are some delicate properties of additive number theory about Cantor set, maybe specifically. If you have another open, so it can make it be easier than for this. But, okay.
You should probably ask Lutz that had other papers on this, but I think the addition is, it's quite complicated, the interaction of addition with randomness.
I tend to agree, but.
I think we're cutting it at break time, so maybe we should thank the speaker.
Okay.